Hi, everyone. Can I ask you guys to stop talking, please? I'm going to Can we turn off the music, please, fellas? Fellas, the video/music. Thank you. I'm going to read through the solutions for 41 to 50 right quick. I know you guys probably spent more time on this than a usual homework since we went over it kind of a second time and then asked you to look at it a second time. I'm only going to read the evens, though, since the odds you're able to check for yourselves. 42 is negative 435 over 106, and then positive 783 over 106. 44 would be 261 over 73, and then negative 696 over 73. 46 was 61.56 pounds. 48 was 95.22 pounds. And 50 was 99.06 pounds. Are there any questions or repeats? Jackie? 48 was 95.22 pounds. Sydney? 46 was 61.56 pounds. Questions on any of these? Okay, so it seems like this went pretty well after getting a second round of explanations there, so I'm glad that helped. Then today we're going to move forward and talk about our last 2D topic. Oh yeah, this is the one test. Long time from now. We still have all of the 3D things to talk about. Well, nobody asked any when I asked 3 times earlier. It's too late now, but I'd be happy to answer your question outside of class, Bella. Well, they all lost their chance by waiting too long to respond.
No, you didn't do anything. I came out right over there. I was probably second one.
All right. So this is our last. Can we stop talking, please? Thank you. This is going to be our last 2-dimensional topic before we move into 3-dimensional topics. So what we're going to be largely talking about in this section is working with the vector equation for a line. So this is really just like an Algebra 1 topic. We've just recast the notation in terms of vectors. But we're doing the same things that we would have done like in an Algebra 1 course, but instead of using like the equation for a line, like y equals mx plus b, we're recasting that equation in terms of a vector equation. So what I'm going to start by doing is introducing some new notation and talking about how we can translate y equals mx plus b into a vector equation. Okay with that plan? Okay. So the first piece of notation is what I'm going to call IB component form. When I learned these topics, we called this just a column vector. But basically what we're saying is the component form AB we're going to write as the column vector AB. That's all. So we're going to write this vector as like a 1x2 matrix. This is kind of how I learned this topic, but it's not uncommon to see this notation with the vertical parenthesis and this referred to as a column vector because it's one column, or as a 1x2 matrix. They're all kind of equivalent notations. So if you're going and Googling on these topics, you might see some different notations used or different vocabulary used. So I'm trying to use all of those different vocabulary right now and talk about there being really the same notation and the same vocabulary. Okay with that? So let's look at a specific example for an equation for a line. Let's say we have something like y equals 1/2 x plus 1. Okay. If you remember back to your Algebra 1 class, if we wanted to write an equation for a line like this, what kinds of information did we need? To write the equation for a line, something like y equals mx plus b, what kind of information did we need to be able to do this? Ben? Okay, so a slope and y-intercept, that's a little bit too specific, but there were some other situations where we gave you some information, asked you to write the equation for a line. 2 points, very good. And then the other situation would have been the slope and 1 point. Everybody kind of remember that from your Algebra 1 class, that these were all the different starting points where we could ask you to write the equation for a line. Okay. So the same is going to happen here for writing a vector line equation. We're going to need a slope and a point. That point could be specifically the y-intercept. There's nothing wrong with using that point. It could be any other point or 2 points. Either of those is going to be enough information. So just to be clear, like this slope and y-intercept is still a subcase of slope and 1 point, right? Okay. So first thing that we'd want to do is we want to convert a slope into a column vector. So for example, in the equation for a line that we wrote up there, our slope was 1/2. The vector that we're going to use to represent this is going to be the vector 2, 1. Why does that make sense? Remember, what is slope really? It's the change in y over the change in x, right? So when we write our vector in this column form, the x-coordinate is the first one and the y-coordinate is the second one. So this should hopefully make a lot of sense as to why we've switched the order there from the fraction to the vector. Because the x comes first and the y comes second. But when we write our slope, the y is on top and the x is on bottom, right? Is everybody okay with that idea? Okay, so that's quite easy. Now, we would want to convert our point into a vector. So let's say that we used Ben's favorite point from this, which was the y-intercept. So that would be the point 0, 1. And I'm going to convert this into the vector r sub 0. Which would just be the point, or the vector 0, 1. Yes? That's the letter R with a subscript of 0. So, in general, our vector equation is the vector r is equal to the point vector r naught plus our slope vector v times some parameter t. Does this look quite similar to y equals mx plus b still? Yeah, it does. So in our specific case that we were working with, we have 0, 1 plus 2, 1 times t. So if I pick a value for t, let's pick a value for t. 3. Great. So if we do that, what sort of multiplication is going on here between this number 3 and the vector? That's called scalar multiplication. How do we do scalar multiplication? We just multiply the scalar to both components. And then this is vector addition, right? We're adding two vectors. How do we add two vectors? We add the components. So what this tells me is 6, 4 is a point on that line. Is that okay? So to graph points, we're going to pick a value for t. T is neither the x nor the y coordinate. T is a parameter that we use to generate points on the line. And because t can have infinitely many values, we can generate the infinitely many points that are on our line. Everybody's okay with that idea? Just to kind of illustrate to you what's going on graphically. So let's say here is our line. When we picked t equals 3, what we did is we found this vector whose terminal point is the point 6, 4. Any vector we find using this vector equation, the terminal point is going to lie on this line. And because t can be positive or negative, we can get all the points wherever they're at, right? Maybe we'll write r with the subscript t equals 3 on it. So let's do another example. Sound good? So let's say we want to find a possible vector equation for the line y equals 3x plus 5. What's the slope for this line? 3. So using that, we can create the slope vector, what? 1 and 3. Everybody's okay there? Okay. Then we need a point from this line. What's a point from this line? Somebody said 0, 5, I heard. That would be fine. So that's going to become the point vector R naught. What is that vector? It's going to be 0, 5. So now I can just write my vector equation. R equals R naught plus V times T. Everybody happy there? This is just one possible answer. Notice we have the word possible here. How could I get a different version of this same answer? Yeah, if I picked a different point, what if we used instead maybe the point 1, 8? Right? That's still a point on that line. So we could get a different equation if you pick a different point, which is fine. Any equivalent answer would be correct. What's another way we could get an alternative answer? What if I thought of my slope instead of 3? What if I thought of it as 6 over 2? That would give me, again, a different version of still the same answer, right? Still equivalent, still correct. So there's many, many possible solutions to this, or different ways we could write this vector equation, any of which would be fine. Everybody happy there? Let's do another example. What if we were asked to write the vector equation 3, negative 1 plus 2, 3t in slope-intercept form? Sure. Oh, not negative 3. Nope. This is the slope vector. It'd be 3 over 2, right? Good. Oops. And that'll allow me to solve for b, right? So we can say then y equals 3 over 2x minus 11 over 2. Good. Is everybody happy there? Is 3 negative 1 the only point you could have chosen? No. No. How could you get a different point if you wanted to use a different point? You could find a point on the line by doing what? Picking a value for t and plugging it into the equation, right? And that'll give you some other point on the line as long as t is non-zero. If t is 0, you're going to get back that point. But any other value of t would give you a different point. Any of which would be fine. Is everybody okay here? So far, how is this?
Not terrible.
No, hopefully it feels pretty easy still, right? This should feel very Algebra 1-ish. We're doing the same things we did in an Algebra 1 course. We're just using the language of vectors to do so. But it's not terribly different conceptually than what we've done in a previous class. The intersection of these two lines. So, how many different kinds of answers can I get to the intersection of two lines? There are 3 different kinds of answers. What are the 3 different kinds of answers I could get? I can get a single point if the lines intersect exactly one time. I could get infinitely many points if the lines are coinciding, one line lying right on top of the other. Or I can get no points of intersection if the two lines are parallel, right? Those are the 3 different outcomes for a problem like this. Everybody's okay with that plan? Okay, so that's the kind of answer we're looking for. Either a single point, a case where we get infinitely many points, or a case where we get no solution because the two lines don't ever intersect at all and they're parallel. So here is the idea and what we're going to do. We're going to build a system of 2 equations to solve for the values of s and t, where these 2 lines, or these 2 equations, have the same point. So I'm going to call that point that they have in common xy, and I'm going to replace the r1 and r2, like the independent variable of my, or the dependent variable of my vector equation, with that point xy. Everybody's okay with that? Now, if I simplify this first equation, if I do this I do the scalar multiplication and then vector addition, I get 2 plus s and then 4 plus 3s. Can everybody see that? And how I got that? Okay. This second equation, I'd get -1 plus 3t, and then 5 plus 5t. Everybody okay there? So what I can say is I have x equals 2s, and s also equals -1 plus 3t. So I can say 2s equals -1 plus 3t. I'm going to move the variables to one side and the constants to another, giving me the equation s minus 3t is equal to -3. Is everybody okay there? Next, I'm going to take y equals 4 plus 3s and y equals 5 plus 5t. And I'm going to set those equal to each other since they're both equal to s, or I'm sorry, y. They can both be equal to each other. And then I'm going to move the variables onto one side and the constants onto another and create a second equation. That's going to form a system of two equations. What's going to be the fastest way to solve a system of two equations?
I know that's not
Set them equal to each other.
Okay, so that's the same thing as substitution.
Oh, canceling on numbers.
Okay, that's elimination. There's still a faster method than that, where I don't have to write anything down. Think back to your Algebra 3-4 class from last year. I would use a matrix on my calculator and use the row reduced echelon form command to solve this.
I don't know. Sorry.
So I'm going to form a matrix. The matrix that I'm going to have has two rows, one for equation 1 and one for equation 2. And it has three columns, one for the s's, one for the t's, and one for the solutions. I'm going to write down the coefficients from each row. So the first coefficient is 1, and then it's -3, and then -3 again. The second row is 3, -5, and +1. Is everybody okay with what I just did? So what I did is I turned this system into this matrix here, and I'm going to perform the operation RREF onto this matrix. RREF stands for row reduced echelon form. Not important that you know what any of those things mean. So to do that, I'm going to exit back to the main screen of my calculator. I'm going to go back into the matrix menu, and I'm going to go to the Math tab. Inside the Math tab, I'm going to scroll down until I see the command RREF. Make sure you take the RREF and not REF. They are two different things. You want two R's, not one. And I'm going to do RREF on that matrix that I just made. Is everybody okay with this? This is telling me my answer now. So if I read the first row of my matrix, what that says is 1s plus 0t is equal to 4.5, i.e. that s is 4.5. If I read the second row of my matrix, that says 0s plus 1t is equal to 2.5, or just that t is equal to 2.5. Is everybody okay there? Wasn't that nice? I didn't have to really write down any work other than writing down the matrix that I used and the result my calculator came back with. That would be appropriate on a test or quiz for you guys. I would not need you to solve a system by hand. Use your calculator, save your time and pencil lead. Okay? Now, is this my final answer? Is this the point? No. What do I need to do? I need to go back to one of these two matrix equations. It does not matter which one, and plug in either S or T, it does not matter which one, into the equation to get the result. So for example, I know that S is 4.5. So here I could plug in 4.5 for S. And that is going to give me that. Did I write down the wrong thing? No. Okay, good. Yeah, so that's what you should get. So your point is either way of writing it. You write it as the vector, if you want to write it as an ordered pair, I don't really care. Okay. So that's kind of a lot of work, but it's not anything that's unfamiliar, right? They're all just using techniques that we've learned before, right? So just to review, what we did is I took my two vector equations and I wrote them as an x and a y equation, and I took the two x equations, stuck them together. I took the two y equations and stuck them together. Got the s's, got the parameters on one side and the constants on the other to create a system of two equations. And I solved that system with my calculator to get a value for either parameter. Really, you only need a value for one of the two parameters, right? And then I plugged that parameter value back into the corresponding vector equation to get the point. Okie dokie. All right. That finishes up 2D vectors. I'm going to start 3Ds today. But really the only topic I want to talk about when dealing with 3D vectors today is the most basic of basic things. So the first thing I want to talk about is the three-dimensional coordinate system. Which is a little bit tricky to draw on a sheet of paper. Why is drawing a three-dimensional coordinate system going to be tricky to draw on a sheet of paper? A sheet of paper is two-dimensional. A 3D coordinate system is three-dimensional. So this is an example of what this would look like. This one, the line that's coming out of the sheet of paper towards you, is the x-axis. This line is the y-axis. And the up and down is the z-axis. Is everybody okay there? So to describe a point in a three-dimensional coordinate system, how many components do I need in my point? I need 3. So instead of my points being described as ordered pairs, like we have in 2 dimensions, my points are going to be described as ordered triples in 3 dimensions. It's going to have an X, Y, and a Z. They are going to be listed in that order. So, for example, let's say we wanted to graph the point three, 2, 5. Is everybody okay there? So to do this, I need to draw 3 tick marks on my x-axis, 2 tick marks on my y-axis, and 5 tick marks on my z-axis. Is everybody okay there? What I'm basically going to be drawing now is like a box to get this point in the correct position. So what I'm going to do is I'm going to draw a dashed line from x equals 3 parallel to the y-axis. Everybody okay there? Does everybody see what I did there?
Is that like a line that you do?
It's just like a dashed line. Oh boy.
Should we draw that or no?
Yeah, you need to draw that. No, that's okay. It's a fair question. And now I'm also going to draw, starting at y equals 2, a dashed line that's parallel to the x-axis. I'm going to make a little point there where they've intersected. And then I'm going to draw a dashed line up to that position on the z-axis. This didn't turn out very well because I don't think I scaled my picture very well. Let's try another one. I'm just going to change this number to a 4 to make it a little bit clearer what's going on here. Well, let's just keep that the way it is. I'll just make a new set. So let's say we want 2, 4, 5. Let's just do this. I won't draw them dashed here. It's too hard probably for you guys to see what I'm doing, right? Is everybody, oh, yes. Sure. So this is like 4. That's 2. And that side is 5. That's a little bit easier to see what's going on. Is everybody okay there? So if you want to see how there's a box here, let me draw this in a different color so it's easy to differentiate. Do orange. right? There's like my box, and that corner there is my point 245. Okay. The notes have some nice computer-generated images in them. If you look at the book pages for this section, if you're having trouble visualizing what I'm doing because my artistic skills are subpar, I understand. I don't take any offense to it. I'm doing the best I can. But the pictures in the text are quite good. But that's the idea. Does everybody feel okay about plotting a point in 3 dimensions? Okay. So, who remembers what the distance formula is in 2 dimensions? Hi, Miss Yarrow.
How are you?
Good. How are you doing?
Doing great.
Who do you need?
I have a pass for Bella. Well, it's not actually a pass, it's a reminder from Mr. Peter that they asked us to look.
Is she naughty?
Well, it's Bella.
Yeah.
So, yeah.
Oh, it's because everybody's too exhausted by the end of the day on Thursday to be obnoxious.
Well, I'm sure if it were my room, it would be obnoxious. That's just, I agree with that.
You know, probably. Everybody, does this 2D distance formula look familiar? Right? What do you suppose the 3D version of this is going to look like? Yeah, we're just going to add a z component. Everybody okay with that idea? Okay. Here's a geometry brain reminder for you. What's the midpoint formula in 2 dimensions? Here's the way that I remember it. It's an average. Yeah. So it's the average of the x's and the average of the y's. That's the way I remembered it. What do you suppose the 3D version of this is going to look like? Yep. So this is going to be a familiar pattern in 3 dimensions. Is we're going to try to make as many of these things just analogous to the 2-dimensional counterpart as we possibly can by just adding in a z component to our calculation. Okay, let's just do a quick little calculation and then let's get out of here. So let's say we have these 2 points. What's the distance between these 2 points? let's see, what's that? 534, I think. Oh, should it? What did I do here? That's fine. Okay, thank you. That's 13. Let's see, 216, 169, 169. Yeah, 534. Okay. Everybody happy there? Okay. What if I want their midpoint? What do you guys think? Not bad? Okay, let's stop here.